Hi, Spark AI Summit. My name's Jason Brown, and I'm a senior data scientist at Astrea. Astrea is a startup in Virginia in the US, and we are working on building cloud platforms and web apps to enable data scientists and other analysts to discover, analyze, and work with satellite and drone imagery, overhead imagery. In this talk, I expect that the audience will be familiar with some of the basics of data science um, and Apache Spark, but probably have never worked with overhead imagery in practice. At our company, our technology stack depends heavily on Apache Spark, and in order to work with this kind of image data in Spark, we have built an open source library called Raster Frames to enable us to do that. And that's going to be a focus of a lot of my talk today. But first, let's talk about overhead imagery. You're probably familiar with it if from nothing else, your Maps app on your phone. It's a very useful way to get around, but there's a lot more to it. We have potentially this imagery as art. This is a print shop. You can buy these and hang them on your wall. They all come from the Daily Overview Instagram account. Beautiful images there. We have this imagery as journalism. It's often very powerful for storytelling. And you can see dramatic changes and know when they happened. It's a very useful and powerful way to explain and understand what's going on in our world. And that kind of thinking about imagery is very common in defense and intelligence. There's a long history of working with this kind of data um, in military and intelligence agencies for the same reasons, to understand who, what, why, when, where, and how. Another community that has a long history of using satellite data in particular is earth science. The sequence of images that you see here come from a satellite called Sentinel-5, and it measures the concentration of pollutants in the atmosphere from space, which is pretty amazing. This is a series of images from the first weeks of 2019 and then the first weeks of 2020 around Wuhan in China, and you can see the dramatic decrease in nitrogen dioxide pollution in that area as they were under a very strict lockdown. So as a data scientist, you look at all of these images and these kinds of examples and think there's a great signal in this data. There's a lot of useful information in here. And the other aspect of that is it's big data. And it's big data in really all of the ways that we talk about the big data Vs. The variety of this data is sort of staggering, not only if you're coming from working with other kinds of data like transaction data or whatever. It's very different, but also even within that community, there's a lot of different names that are used depending on folks' background. There's a lot of different file formats at play. There's a lot of different ways that folks have published this data in the past. The velocity of the data is pretty astounding. There's one mission run by European Space Agency called Sentinel-2. It's a pair of satellites that work together to image the entire landmass of the Earth every 5 days. And that generates about 6 terabytes of imagery every single day. There are also government operators of satellites in the US, Japan, and other countries, as well as many private companies, small and large. So in total, there are hundreds of satellites that are taking images of the Earth every day. And on top of that, we have an unknowable number of drone operators that are doing this, taking these kinds of images. So from all of that velocity, you get very high volume of data. This chart that I'm showing you is a couple of years old and shows this exponential growth in the US NASA archives. And at that point, it was approaching 30 petabytes. So there's certainly a lot of this data, and it's becoming more and more accessible in the U.S. and in Europe. There are open data policies that govern most of the science data that they produce and collect, and there are also very significant efforts in the community to create open standards for how this data is accessed and cataloged in the cloud, which is really exciting in terms of really democratizing access to this data. So what about data science? All of the signal in these sequences of images, all of the imagery that's available. At Australia, we started looking around and said, what can we use to really exploit this data? And I'll highlight one library that's very important to how we do this. It's called GDAL. It's very mature, and it has, it's really a lot of low-level operations on file I/O and transformations on the data. You need to be able to do that to process this data, but in our view, it's not enough to really do the things that data scientists want to do. So RasterFrames comes about when we ask a couple of questions. One is, what makes this overhead imagery data special, and what affordances can we make that we can bring to bear for processing this data in generalist tools? And here I'm talking about really Apache Spark. So let's answer that question, what makes this data special? Let's start from the data scientist's sort of mental model of any image. If you're using Python PIL, or if you're working with a deep learning library, you pretty much have an array, a multi-dimensional array or a tensor of data that's three-dimensional. It's height and width and a number of channels. If it's one channel, it's grayscale. If it's three channels, it's red, green, and blue. So starting from that idea, overhead imagery is different in sort of how it's published and what you find in practice. The images tend to be enormous, like 100 megapixels or larger. And each channel is typically going to be much more information, 16 bits per channel. Channels may be stored in different files. There's often many more channels. I mentioned Sentinel-2. It has both ultraviolet and infrared data that come to 8 or 10 bands. So on top of those differences, there's important other factors to consider. The location that the image is describing is very important and is key to helping us understand how this data interacts with other data in our analyses, right? So we need to understand how that location data is described, and we need to be able to make sure that we track it closely. And the second thing is there's a lot of other metadata attached to each image. Things about when the image was acquired, by what sensor, who processed it, and so on. And then there's oftentimes some special metadata that help us understand exactly how to interpret the values in the array. So we'll dig in a little bit more on that idea of location. To understand the location of a overhead image, we need to know about two things. The first is a projection, or CRS, and I recommend the video that I have linked here. This poor gentleman is trying to take a globe and turn it into a flat map. And that's basically what a projection or a coordinate reference system does. It's basically an algorithm that helps us turn a 2D coordinate system point into a location on the surface of a 3D Earth model. Unfortunately for us in practice, that's going to be just a string that names the algorithm and maybe gives a couple of parameters. The next thing that we need is a slightly scary sounding thing called an affine transform. And basically all that does is tell us how to go from the tensor space, the array space, into our CRS 2D coordinate plane. So if we have those two things, the affine transform and the projection, we can go from the tensor space, like the pixel, to a arbitrary 2D plane, to 3D exact location on the 3D surface of the Earth. And in general, we represent that transform. We can do that with just the southwest and northeast corners of the image, if we know which image we're referring to. So we take all those things into consideration, and we propose in RasterFrames and implement the following data model. If you look on the left-hand side here, we have what's sort of like a physical model of one really large image. This might be like a 100 megapixel image, and it has 4 channels represented by the different colors that you see. And we're going to take that really large image, which is too big to really effectively process in a Spark task, and we're going to break it up into smaller sections, and we're going to call them tiles, right? So each channel is going to be broken up the same way, and each tile is going to be a value in a row of our Apache Spark SQL data frame, with a different column for each channel. And then we have the associated metadata sitting in other columns that we can then reason over. And we propose that this is a very powerful data model, not just for one image, but in cases where you have perhaps many images that cover different times and slightly overlapping locations and other things that are not homogeneous. As those things are captured by the columns, we can then start reasoning on them in a really powerful way. So the whole idea of RasterFrames is taking that data frame model and making it a practical reality. The first thing that we do is we want to have that be practical reality for data scientists, and that means having a really strong Python API. And we have a custom data source to read this data, which includes, like, under the hood GDAL as a way to read raster data. We have a tile UDT, a user-defined type that basically carries the array tensor, or the tensor or array of the image data, as well as the location data for that small section of the image. And in Python, when you bring that over to the Python driver, we see that basically as a NumPy int array, which is about what you'd expect. And then in RasterFrames, we have about 200 different column functions to operate on either the location or tensor elements of tiles, and work with other related types. And so we'll give an example we'll give a code demo in a few minutes to show what that looks like. We also have Spark ML transformers that help us use this tile UDT in our Spark ML pipelines. And then we have some support for writing out and visualizing a tile UDT. And in particular, that is important in an IPython or Jupyter context. And so that's what we're going to do next. We'll show you a live demo of this. And if you go to my GitHub gist, you can see the notebook code that we have for this, as well as some supporting data files. All right, so here's our demo notebook. So here's our demo notebook that you can find in that gist. And what we're going to do is we're going to read a data set from Kaggle. It is the California wildfire incidents from 2013 to present. It's one CSV file with 1,600 rows, and you can see the columns here. We have important to highlight a longitude and a latitude, so a point location for the fire, and then a number of acres burned. We defined above a function that's going to basically help us create like a bubble around that point location that's about the same area as this acres burned. You can see the other kinds of information that we have. Some of it's administrative, some of it's about the resources that were used to fight the fire, and some of it is about the damage caused, injuries, fatalities, a number of structures affected by the fire. So an interesting data set, and we're going to try to find some satellite data to enhance what's here. So we'll do some. We have a few functions here to clean up a few things, and then we're gonna select down just the 2019 fires here to help this thing move along a little more quickly. So we're gonna look up some satellite imagery using the my company Astrea's Earth AI proprietary library. The Jupyter Lab notebook that we're in right now is called Earth AI Notebook. You can get a free trial of that to run all of this code if you want yourself on our website. We'll have some details later. The first thing we'll do is look for collections that are available. We have maybe a dozen different satellite missions that we have data about. And this one that we're showing here is called MODIS MOD 11A1. It's land surface temperature, and basically you can think of it as a thermal camera that's pointing at the Earth, and it's imaging the Earth, I think, every day and night. So it's quite quick in its revisit. So here we can see the bands or channels that are associated with that mission. We're going to use the land surface temperature daytime channel and leave the others as an exercise for you to explore later. But you can see some of them are metadata related to the image, and there's also a nighttime temperature. So the next thing that we'll do is for every fire that we have that our geometry bubble, and we have a start date from our Kaggle data and a date that it was extinguished. So we're going to query this catalog and ask for any image from MOD 11A1 that is intersects with that bubble and is in between those start and extinguished dates and has a low cloud cover. And then if you don't want to worry about doing this or get into the proprietary libraries, I've saved this like result as a GeoJSON file, and that's attached to the gist as well. So you can start from this point if you'd like. We have the catalog of data that we've read from Earth on Demand. It's basically, we have the unique ID from the Kaggle fire data. We have the date that the image was taken. We have some metadata about it, in this case, the projection of that data. And then we have the land surface temperature is here represented as a URL. It's a link to a S3 object. So the next step that we'll do in our analysis is we're going to just merge our Kaggle fire data with these image URLs and the other image data. And finally, we'll get into Apache Spark. And we'll do spark.read.raster. We're going to read this merged data frame, and we're going to tell it to treat the LSTD column, this column of S3 URLs, as the images that we want to read. So it's going to create a lazily evaluated tile column from that path, and then it's going to store the path in a new file. So you can see our schema has this tile column. It's a structure that has the tile, the CRS, and extent, as we discussed before. And then we have these camel case fields are from the Kaggle data. And then below that, we have the snake case fields, which are from our Earth on Demand catalog. So information about the images themselves. So now our data frame is one or more row for each fire, depending on how many images we found. The next thing that we need to do, and we'll get into the details, but we use some of our column functions to limit the number, or to limit our data frame to only the tiles that intersect with our fire bubble. That's what this dfgeom field contains. And then we'll see that we have 625 rows remaining in our data frame. Now we can quickly inspect the data frame. This is part of our RasterFrames library interoperability with IPython. So our tile column is rendered as an image. The clear portions of the image you see are like where there's missing data. They could be due to clouds or pixels that are over water. You can also see we have some details about the fire, like the name and the date that it started and was extinguished. And then we have some other details about the location of the image and the date the image was taken. So this one was like the second day of the fire, this hill fire. We can also take a look at an individual tile in the Python driver. You can see that under the SQL row, it's just a masked array. It's a NumPy masked array, and it's a unsigned 16-bit integer. A masked array, if you've never worked with them, is basically an array with a binary array of the same shape alongside it that tells you where the values are missing. So from this unsigned integer, we want to get the temperature data in Kelvin. And in the metadata for MOD 11A1, we can find that we multiply those integer values by 0.02. And that's what this RasterFrames column function will do. It's going to basically do a cell-wise multiplication. And now we have a new tile column with that data. And then to finish up our example, we are going to make an aggregate across each fire. We have some of the fire columns that we'd like to group by and select. And then I'll draw your attention to our aggregate. The rfag_stats is going to operate on that tile column, and it's going to do for across all of the rows in the group and across all of the cells. It's going to find things like the minimum value, the maximum value, and it'll report some things like the number of cells that had valid values and so on. So we'll bring that we'll do that calculation and bring it into a pandas data frame and then show you the summary of that. And take just a moment here. Here we go. And so you can see we have some demographic information about the fire, and then our maximum temperature reading. So that's the maximum from all of the images that we had across any of the cells that pixels that intersected that bubble. That's the maximum temperature that we have. And then we have some other details. Some of them are pretty sparse, but we have some other details from the Kaggle data about some of the resources and effects of the fire. So with that, we're ready to wrap up, I think, and invite you to come check out our project. It's under a commercial friendly license, Apache 2.0 license, same license as Spark, and under Eclipse Foundation Location Tech, which provides some IP governance. You can check out the project's website or look for us on PyPy. You can go to Estrella's trial to get a free demo of that notebook environment that we were just using. And we'd invite you to come with any questions or ideas to our Gitter channel or to our GitHub page for issues or look at pull requests. And thanks very much for your time, and we hope to see you on our Gitter and other places. Thank you.